Hi James, I'm going to go through the last four problems in this section. It says for these 41, 44, 50, and 51, find the real zeros of f, use the real zeros to factor f. Okay, so in order to do this, I did it as explained in example 10 on page 248, which goes through basically all the steps of the things you've already learned, or most of them, and then you graph it, and ultimately you figure out what the zeros are by running a couple tests on them. And once you know what the zeros are, then it's pretty easy to factor. So anyway, I don't know if you have to actually do all these steps to answer the problem, but it's instructive to do it anyway. So that's the way I went ahead and did it. All right, so our first function is problem 41, x cubed plus 2x squared minus 5x minus 6. So for this one, the highest order term is a 3 there, so there are at most going to be 3 zeros in the function. And then you do the variations in sign thing. So you can look at this. F of x has one variation in sign that happens right here when it changes from positive to negative. So there's going to be one positive real zero. And if you check f of negative x, I think that's going to have two variations in sign when it changes from negative to positive there, and then it changes from positive to negative there. So it has two variations in sign. Therefore, there are either going to be 2 or 0 negative real zeros. Okay, this is a polynomial that has integer coefficients, so you can use that one theorem to be able to determine what the rational zeros are. Remember, you take the last term, which is the 6, that's your a to the 0 term, and then you take the coefficient of the first term, which is your a of n term, and you figure out what the factors of each of those terms are. In the case of 6, you're going to be able to have factors of 1, 2, 3, and 6, plus and minus of each. And in the case of the a of n, just 1, the only factor of it is going to be 1, so it's plus and minus 1. And then taking these two things, AO and AN, you just determined, you figure out the possible rational zeros, which is P over Q, and you kind of go 1 over 1, that's going to be 1 plus or minus 1. You can have 2 over 1, that's going to be plus or minus 2. Same thing, 3 over 1 and 6 over 1, all of them plus or minus. So you end up with these as the possible potential rational zeros. And then you find the bounds of it. And remember, to find the bounds, you take the again, you take the a of o term, but you count all the terms up except for the very first one. So you take the x term and the x squared, but you don't consider the x to the third term when you're counting the bounds. So you take the maximum of 1 and 6 plus 5 plus 2, and that's going to be, obviously, the maximum of that one's going to be the larger one over here, the 6 plus 5 plus 2, which is 13. So you put that there. And for the second one, it's 1 plus the maximum of all of the coefficients, and that's going to be 6 plus 1, so that's going to be 7. You take the smaller of those two numbers, which is 7 in that case, and that tells you that your bound lies between negative 7 and 7. So I went ahead and plotted the function with those boundaries. And here you can kind of see, just from the graph, what the zeros are. You have a 0 at negative 3, you have a 0 at negative 1, and you have a 0 at positive 2. So I wrote this down here, step 5. It appears to have zeros at negative 3, negative 1, and negative 2. You confirm that by using that very first theorem of the chapter, which was, let me see what it was called. Yeah, the factor theorem on page 240. So basically, you check each of these terms by plugging them into the function. If you end up getting if the function equals 0 when those particular numbers are plugged in, then you know they are actual zeros of the function. And so you can confirm that. I guess I didn't actually do that here, but if you do it, you'll see that they all equal 0. And therefore, x plus 3, x plus 1, and x minus 2 are all factors of f of x. So you can just put them together and show it. F of x factored is going to look like this. X plus 3 times x plus 1 times x minus 2. And if you expand that out, you'll see you'll end up getting the original polynomial which you were given. up here. Okay, so I did all of these problems basically the same way. I might not need to go through all of them, but I'll go ahead and, because it's basically all written out here, but I'll still go ahead and do at least one more, and then maybe you can just follow the rest by reading along.